So our last day of Chapter 12, Techniques and Applications of Quantum Mechanics. I sent you an updated version of this. I don't know if anyone noticed, but I don't know. It may or may not help. But you have we're talking about a different type of momentum. We're talking about angular momentum, and that's why I brought in the bike wheel here. Why does that guy walking along the shoestring there, why does he have the big long stick? Balance, yeah. Why is it so long? We're going to see if you wanted I think we're used to linear momentum. That big long stick is for angular momentum. We're used to linear momentum. Football, right? You want this guy to run through all these other guys, right? Well, what characteristics would you want him to have? Really only two choices here. Make him really what or really what?
Fast.
Really fast, that would give him linear momentum, or really big, right? Hopefully both, right? But those are your two choices. And the idea there is things just keep going, right? Or think of it this way. Things keep going, it's hard to get them to stop. It's hard to change that state, whatever it is. So now you got a guy walking on this tightrope. Well, he doesn't want to change his state, right? So it's kind of like in the linear momentum idea, you got this big, massive speed thing going. It's going to be hard to change it. Well, here, angular momentum is just something you're not used to. The equation for it is L equals mvr. I mean, it even has a weird symbol. And it's a cross product. You remember your physics, cross products and dot products. But the point is that R, if he has that radius really big on this angular motion, he's got a lot of angular momentum. You're going to have to, so a torque is the other word. You've heard of torque wrenches, you got to really torque those things down, or it's a twisting force. So by having that length really long, he has to apply a really big twisting force in order to actually move. Because it's an angular motion. Angular momentum's, to generate that angular momentum, L equals mvr. So he has to really, since it's so long, it gives him a lot of angular momentum, a lot of twisting forces necessary to make that thing move. See the trick? So it would have helped too to have that stick really massive, but he has to walk from building to building. He's going to get his little arms tired. Okay. So rotation and a couple dimensions here. So there's our phi. Remember, phi can go from, the diagram's kind of a hint. Phi can go from what to what? 0 to 2 pi. Okay, so that's what we're kind of plotting this wave function on, and they're just trying to tell you that we're talking about circular, kind of like a wave function on a circle, and it has to be on that black circle there, this wave function. Well, if it's going to start, I don't know, if it's going to start here, it winds around, does its thing, woo, it better end up there again, otherwise it can't wrap around. And that's all they're trying to say here, is you've got the top one, A, it starts out at 0, right? 0 and 2 pi are the same angle, but it ends up way down here. So it's not overlapping. This would be an example of an unacceptable wave function. It won't work. But the bottom one will, because it just keeps overlaying itself. Okay. And that's about the only diagram they have on acceptable and unacceptable wave functions for rotation. And I gave you this equation already. What are the little arrows again? Who remembers this? Vectors, right? Okay. M is mass, a scalar. Mass of what? All this stuff is talking about rotation of what? What's supposed to be going in this circle? Yeah. They're gonna try to get into bonds and that kind of stuff. So all they're really talking about is a electron. Right? So all of this is for the motion of one electron. That's what all this stuff is. It's the entire, everything we're going to talk about today. It's the motion of one electron. Okay. So angular momentum of that electron, mass of that electron, right? Its velocity, its distance. What's the cross mean? I don't know if you remember this stuff. Work was a dot product. I don't know, this is probably getting to be too much. But whoa, what happened there? Work is a dot product. So you ended up with a scalar. Cross product, you end up with a vector. Now, Melissa, do vectors have a direction?
Yes.
Yes. So that's therefore cross product. I kind of think of it as right-hand rule. Cross product and right-hand rule are the same thing. So there has to be some way to figure out what's the direction of this final answer, this angular momentum. Well, you're supposed to use the right-hand rule. So what you do is you wrap your hand in the direction of this V cross R, right? So, or just look at the motion. Here, see the little arrow? It's going like this. So you wrap your hand around it, right? And your thumb is pointing. It has to be your right hand. And your thumb is pointing in the angle of the angular momentum. So did the author screw up? Right? Wrap your hand. Has to be your right hand. Your thumb's going down. Right? So the guy should say, whoops. There's no LHR. It's RHR, right hand rule. So you got to do that. That's your L. Right? If it would have been going counterclockwise, then he would have been right. Okay. Okay, now did he do this one right? Okay. Did you do that one right? Can you see the direction of the motion? Do the right hand rule? So the little blue arrows pointing in the right direction? It is, yeah. So instead of using big L, now they're replacing it with J. And instead of having V, they wrote a P. How can they write a P? P stands for what? Momentum. Does this look like momentum to you?
Yes.
Yeah. So because P is M times V. If V is a vector, well, so is P. So that's why they kind of substituted it in there. And you're going to see J. They just get used to it. They're going to write J for angular momentum. Okay. And they're going to use L for angular momentum. Okay. Okay, so now, do you remember this kind of stuff? M sub L is 0, 1, 2. What's going on here? M sub L. They're jumping ahead, man. I wish they wouldn't do this, because we don't get to our wave functions until we get down here. And you have which element can be solved by the Schrödinger equation? I mean exact. There's no guessing, no assumptions, nothing. You can solve it exact. Hydrogen. See, we had all these hydrogenic orbitals. We had 1s, 2s, 3s. Remember all this? And then we had little n can be 1, 2, 3. We had also had what other little quantum numbers? We had little n. We had little L. And it wasn't an L. It was a cursive L. Remember this? And then you also had you had S. Well, yeah. Well, then you have S.
MS?
You had little ms probably, right? There's one more. You had L and little m sub with a little L. Remember this? Okay, so those were our quantum numbers that they came out of for the hydrogen atom. Well, they're using them again, which is fine, because what we're going to do is, what they do is they generate their wave functions. Remember doing this? By having a weighted sum. So let's just put in the solutions to the hydrogen atom, put those orbitals in here, right? And just change the coefficients until you get the best answers. So that's where this little L and M sub L stuff is coming from. And then they figured out, look how ugly this stuff is getting already. They figured out the wave function for you. Depending on what your L and M sub L are, they're telling you what they are. So jumping up here, they are already assuming that, hey, okay, you know all this already, that we solved the Schrödinger equation for this electron, and M sub L and little l, and so they're just trying to give you some ideas here and how they would look. What? All right, let's leave it. Let's wait till we get to the better pictures. We'll just leave it at that. That you measure how M sub L could be 2, 1. If L is, what could M sub L go from? M sub L goes from
0 to 11.
Whoop. Does anyone remember this? Oh, L. Let's start with L. L went from
1.
Yeah.
Negative 1. Oh, 0.
Remember 0 all the way up to
4.
n minus 1. But I don't think you need to worry about that one. The one that's the big deal is this M sub L. And it depended on what L was. This is the one that's important. M sub L goes from negative L all the way up to positive L. That's where these numbers are coming from. 2, 1, 0. Okay. And they're trying to show you what they plotted out the wave functions to show what they look like. Okay. So instead of 2 dimensions, let's talk about 3 dimensions. And since we're not talking about translation really anymore, we're kind of making a shift. I don't know if you realize all this. We had kinetic energy. In the concept preview, we talked about that. The kinetic energy was p squared over 2m. I don't know if you remember messing with that. And now we're just talking about rotational motion. So the kinetic energy is going to be, I'm just kind of giving you some, we're talking about rotational motion. So now we need angular momentum squared. Angular momentum squared divided by 2, and I is the moment of inertia. And there's an equation for it. I is what? mr squared. Yeah. And then what's called the moment of inertia. Right. So this is kind of the route we're heading now. We're trying to move from XYZ stuff, translation, to spherical. And thank goodness we don't have to do all these integrals and stuff. We're going to do some simple ones, but. And they're trying to say that this del squared, where was that? Remember seeing h psi equals, how do you finish this, Gloriana? H psi equals the Schrödinger equation. It's in general. H hat psi equals,
Little omega psi.
we had little omega, but they wanted to they gave a symbol for it because it's h hat, so you always get the energy operator. You always get
E psi.
yeah, E psi. So that's just the general way of writing the Schrödinger equation. The reason why I'm just trying to help you to link this to the past, h hat was del squared. H hat had del squared in it. So you can have del squared and xyz, which is going to be horrible. We can't, I mean, it's ugly enough with spherical polar coordinates. So let's write del squared in terms of spherical polar coordinates. Well, then you've got this, they separated out all the r part, and then they have the angular part. In the angular part, they call the Legendrian, right? Look how beautiful this is getting. And this is in the other, you don't have to write all this stuff out if you don't want to. This is all in the other handout. But the Legendrian is all the angular component. Okay. So we're just kind of introducing a third dimension. So here's the one we had before, right? Phi going from 0 to 2 pi. Now we're introducing theta. Theta goes from what to what? 0 to pi. All right? And r goes from 0 all the way out to infinity, whatever you want. Okay. So now we're back into our 3 dimensions. So that Legendrian is this symbol. Okay. And if you're following along in the book, this is around page 333 or so. If you actually need to get that equation and if there's a typo or something. Okay. So our spherical harmonics, table 12.3. And here's our wave functions, our spherical polar harmonics. They like to write this, L, comma, m sub L. So you pick an L and an m sub L, and then you can just go ahead, see here's the table, L and m sub L, and then you get your spherical harmonic wave function. Okay. And they're all nice and normalized, and everything's all good to go. What else do we want to mention here? I think let's just jump over to here. Space quantization. This is what gets kind of odd. The blue arrows are supposed to be showing what again? Angular momentum, right? And you can give that symbol JZ or symbol, L, whatever you'd like. But on page 335, they talk about this, and they say that you can get that length by saying L times L plus 1 square root h bar, right? Well, h bar squared over 2I. Sorry, that's something else. Just to give you some heads up where things are coming from. That we're talking about rotational motion, 3 dimensions, and there's how you can calculate the energy. E is L times L plus 1 h bar squared over 2I. And I was that moment of inertia. And this is all about electrons, a single electron. Is m sub L in that equation? No. M sub L's not there. Well, but yet, if you pick an L, how many m sub L's can you write? You list them from negative L all the way up to positive L. Look at all these drawings here. These drawings are for, all of them are for L equals what? Can you see it?
2.
L equals 2. Can you see that, Alyssa? They're for L equals 2. Because you have a 2, you have a 1, you have a negative 1, and a negative 2. So you have 5 different m sub L's. Yet they all have the same energy. They have to. Because I want to calculate the energy, I use this equation to get it. Where'd that equation come from? Just look at page 335 and it'll derive it for you. But what's the word for this? There's the D.
Degenerate.
Degenerate. It's degenerate. All of these orientations in space are degenerate. space quantization. So that means this electron spinning can only be oriented, its angular momentum can only be oriented in certain directions. If we're talking about angular momentum in the first place, I think this is a good example, right? If I'm spinning this, and I get that spinning around really, really good, where's the blue arrow? Right now, where's the blue arrow? How would you draw the blue arrow?
You're holding.
Okay, and it's pointing, okay, good. And at the pointing, so it's spinning like this. Where is it pointing?
This way?
Okay, is it pointing that way or is it pointing this way? Use the right hand rule. So it's pointing toward that. So it's coming right out this axis and going that way, right? If I spin it this direction. Okay. So they really don't care about the path of the electron because you don't know the path of the electron in the first place. So these whole circles and things, you're not supposed to think of them at all as the path of the electron. No. There's just angular momenta in this system due to this motion. And that's what you're supposed to think of. So it's kind of best if you don't even see these circle doohickeys, okay? Because it's just angular momenta. But the point is orientation. How could orientation in space be fixed? Well, yeah, it's angular momentum. You have to apply a torque to change it. So, and I can apply a torque to change it. Okay, I have to twist it. Okay, and then it'll stay there. Now the weird thing is I can apply whatever torque I want, a little more force, and get it to stay at that angle. With an electron, can I get it to do this at whatever angle I want if it was an electron? If this was as small as an electron? No, it's space quantization. You can't. It's only certain angles. It's really funky and weird. Nobody knows why, all right? But it works. It gives the right answers. All right. So have you ever felt this? Gloria, hold this.
Do I
All right?
stand?
Yeah, you better, right? And just grab the handle
Okay.
and try twisting it.
Twisting it which way?
I don't care.
Okay.
It resists
That's
it.
weird. Whoa. I don't know what to do with it.
Just set it on. It'll stop it there. It's hard. It's hard, right? It resists
You're
it.
crazy on me.
But if you want, you can play around with that after class. It's something to experience, to actually feel that. Otherwise, you wouldn't know. It's really hard to imagine. But so let's see. I don't want to skip anything here. So what we need to do is they call these projections, and we're going to learn how to draw them. But before we learn how to draw them, this is really the best way. It's really the best. It's the best image because it doesn't. It shows because it showed the natural motion. I guess we should keep track of these. What things you can actually see in our big world that also happen in the microscopic world. You just witnessed another one. When I spun it at some angle and put it there, it started doing what? It started doing this, right? The whole wheel starts. It's a P word. What's the P word? I can't get it to stay there. It keeps going. It stays at that angle, but it goes in a circle. Precession. Big deal with NMR, man. A lot more frequency. Is bringing back nightmares?
Yeah.
Mel and Al wouldn't know about this yet. Gloriana, you had instrumental.
No, I haven't.
You haven't?
No.
I thought you did.
Taking it next year.
Okay, well, you have an excuse then.
Okay.
So, precession. That's why there are these cones. The angular momentum is in those, has to be in those cones. Are those cones at different energies, Jeff?
No.
No, they're all degenerate. There's space quantization. Okay. So how do you draw these things? Well, if you're going to draw them, you need to know what L is and what M sub L is. Otherwise, you're not going to be able to draw these. You need to know what L is, and you know what M sub L is. And then once they tell you what L is, Well, if they tell you L is 1, you're going to be drawing 3 of these because there's 3 different m sub L's. Make sense? So how do you draw these? The length of the arrow is the square root of L times L plus 1, h bar. That's the magnitude of the angular momentum, the square root of L times L plus 1, h bar. So I think the homework question wants you to draw it to scale or something, so you just make 1 centimeter be 1, right? 1 be 1 centimeter or something. You'll see. Just play around with it. I'll be glad to help you when you get that. Maybe we can get that far in the homework today. But the length of the blue arrow is the square root of L times L plus 1 h bar. Actually, it kind of looks better. That's why they kind of use the J, because you're going to be talking about different quantum numbers. So it's, in essence, it's J times J plus 1 square root h bar, because then it'll always work, especially when you start talking about molecules and things instead of just single electrons. But anyway, so I'll put it back how it was. So that's how you draw the length of the blue arrow. Then notice how plus 1, plus 1, plus 2, oh, it's twice as far. Negative 1, it's going down a unit of negative 1. Negative 2, it's going down a unit of negative 2. So they're trying to say that your arrow, your axis that you're always drawing here, that's the z-axis. They had to give it one of them, right? It's space quantization. So we have to arbitrarily name one axis. Well, we're going to name the z-axis. Everything is going off the z-axis. Fine. So what is the z component? The z component is always m sub L h bar. It's always the z component. So if m sub L is negative 1, then the z component's going to be negative h bar. That would be this one. See that? So this distance right here, that's negative h bar. This distance right here on the z-axis would be what? 2h bar. Over here would be h bar. Then you left. Oh, how about this one? 0. There is no z component because it's m sub L times h bar. Well, m sub L is 0, so there is no z component. Okay. So these are called projections. I think I may have mentioned that. Right? They allowed orientations in space. Okay, I think we've got everything covered here. Okay. Fermions and bosons. They're still kind of sticking with this idea. The string theory hasn't fixed everything. So they're still working on that. So we're sticking with this. We have fermions and bosons. You ever hear this? Fermions are what's supposed to make up all matter, everything. They make up all matter. And bosons are what hold matter together. So if fermions make up all matter, and bosons are what hold it all together, which category does, which one essentially consists of electrons and protons? Yeah, fermions. That's what makes up all matter, electrons and protons. And then bosons, that's what, like photons, that's pretty much holds things together. So fermions follow the Pauli exclusion principle. Bosons do not. What was the Pauli exclusion principle? Do you remember doing this? Like you were filling in these orbitals, like you had 3p. Oh, if I had 3p, how many orbitals do I draw? 3. But I can fit 6 in and max it out. 3 because there's 3 different values of. Anybody?
Yeah.
Well, oh, L is 1. That's why I drew a p. M sub L, because M sub L goes from negative L to positive L, so negative 1, 0, 1. So that's why there's 3 orbitals. If I want to, remember we drew these arrows with lines with arrows on them to represent these electrons, whether they're spin up or spin down, the only 2 choices you had. What could you draw and say and break the Pauli exclusion principle? And Smith would say, "Oh, that's wrong. You just broke the Pauli exclusion principle."
Draw like 1, 2, 2, or you skip 1.
Put 2 and 1 without putting, yeah.
Remember, they're degenerate. Doesn't matter. They're all the same energy. So this is okay.
Putting 2 in 1 orbital.
2 of the same spin, 1.
There you go. 2 fermions that have the exact same set of quantum numbers is breaking the rules. 2 fermions cannot have the exact same set of quantum numbers. That breaks it. So we have electron spin. Again, try not to think of electrons spinning and now I've got right hand rule. Just think of it as a system, and this system has angular momenta due to the electrons themselves, their motion and their intrinsic motion. So that's the spin, and you can actually calculate the spin angular momentum. This is where, remember I said the general rule kind of works, where you had, if you want to draw the length of the arrow on those projections, here it is, right? Just have a J in there. So instead of talking about angular momenta here, right, orbital angular momenta, let's talk about spin angular momenta. Well, then you just put the little spin quantum number, s times s plus 1, square root h bar. So it just fits in the general trend of things. And that's about it. So any questions? We can get started on this stuff. .14. Here's a hint. All right, we're doing A exercise 14. Hint, the only variable of integration is phi. Well, let's see what the question is. The wave function, psi of phi, for the motion of a particle in a ring is of this form. Determine the normalization constant. What is this thing? Can you read this? Psi. What's the big N doing there?
The normalization.
That's the normalization constant, right? So we got to figure out what that is. That's what we're after. And then it's E to what power? Can you read that?
IN.
You got the I.
Oh, M sub L.
M sub, that's supposed to be an M sub L. And then times our phi. So how do we set up normalization again?
1 equals the integral psi star psi d-tau.
1 equals the integral psi star psi d-tau. Okay, that sounds like a good starting point, Jeffrey. Now what?
Plug in the psi
Okay, so you'd write what?
Well, for psi star, n e to the
1 equals,
integral.
oh, integral from what to what? And the only hint you have is, well, you have 2 hints, I guess. One is the only variable of integration is phi. And the other hint is it's phi.
0 to 2 pi.
So it goes 0 to 2 pi. Okay, now I keep going, Jeffrey. What were you saying?
N e to the negative I m sub l.
Good, and e to the negative I m l phi. Times, Kevin?
And e to the, why is it negative?
Because the I
Oh, the I.
with the star.
Because of the
Oh, yeah, yeah.
complex conjugate, exactly.
So then
Because of that guy.
this would just be I m sub l phi.
Yes. D phi. Okay, Alyssa, now what?
Or you can pull out the ends.
Pull out the ends. Good idea. N squared.
The integral of 0 to 2 pi. And then, could you combine the e's?
Yeah, can we? Can you do that?
Yeah.
Yeah. Because it's the same thing. It's like 2 to the x times 2 to the a. Well, that's 2 to the x plus a, right? Does that work? So we'll end up with e to the 0 d phi. All right, well, I think you can finish that one.
So we don't have to do the other 3, like dr.
That's why I had to give you that hint, because when I started doing this problem, I was doing the whole thing. But if I wanted the answer in the back of the book, so they should have said 1 dimension. And I guess they kind of did, because they, in the homework question says this. It's a function of phi and phi only. But Jeff, it doesn't follow. It's not consistent, because before they did the exact same homework where they just had an r in it. Well, then you're supposed to realize, oh, it has a theta and a phi in it too, phi tau, right? Remember doing that?
Mm-hmm.
So that's why I had to give you this hint and say that, look, the only variable of integration is that. So d tau is just d phi. That's it. Stop there. Okay. So next one. A point mass rotates in a circle. I think that's, you're supposed to say, realize that that's a, not an I, but a, that's supposed to, yeah, right? I don't think, I gotta somehow fix these. It's supposed to be a little L, right? Calculate the magnitude of its angular momentum and the possible projections of the angular momentum on an arbitrary axis. So calculate the magnitude of the angular momentum and the projections on an arbitrary axis. What they are talking about is this stuff. Clean this up. When they say the magnitude of the angular momentum, if we're just focusing on this, I'd say, hey, the magnitude of the angular momentum. What would you be? What would I be referring to?
The length of the arrow?
The length of the big, thick blue arrow. Exactly. That's the magnitude of the angular momentum. Okay, I'm not talking about the magnitude of the angular momentum. I'm talking about the projection onto an arbitrary axis. Now what would I be talking about in this diagram?
The direction of the arrow?
Mm-mm. Remember, I kind of gave you a hint. This z-axis, they just had to pick one. Doesn't matter which one, just pick an axis. We need to pick an arbitrary axis. So we just pick z. And our component on that z-axis was always what? On that arbitrary axis, our component is
H bar,
h bar times
M sub L.
m sub l. That's our projection onto an arbitrary axis. So when they're talking about the z component, if you pick z as the arbitrary axis. So once you realize that, this problem isn't so bad, right?
It would just be H bar 0, negative H bar.
Yeah, those would be the projections. And then for the other one, it's going to be what? For the magnitude, you'd be what?
Would be the square root of L times L plus 1 times H bar.
Yes, which is going to be
Square root of 2 H bar.
square root of 2 h bar, so. Yeah. Man, you guys are flying. Keep this up, won't have any PChem homework. Oh, here's the one I was talking about, drawing this stuff. I knew there was one in here. Okay. Again, these guys should be L's, right? Little cursive L's. Somehow I can't get it to work so good, so. Okay. Draw scale vector diagrams to represent the states. We didn't call these vector diagrams. We called them, start with a P. We called them projections. We call them projections. Same thing. Vector diagrams. We call them projections. So we had some arbitrary axis. You had to draw the magnitude of whatever type of angular momenta they're talking about, whether it's spin or orbital. Right? It's supposed to be an L. Right? Here we have we have a spin. Here we'll have an orbital, another orbital. Yeah, but they want it to scale. So when you go through and you calculate this stuff, remember the component on the arbitrary axis is m sub l h bar, right? I might just say, I don't know, like you're going to have things like a half h bar. You're going to have things times, just make it in terms of centimeters. That's how I did it. If I got my angular momentum to be 5.5 h bar, well, then I just made the length of my arrow 5.5 centimeters. Right, that's somewhat to scale. Make sense? That's how I did those. Alyssa, to see how I do these?
No, can you say that one more time?
Okay, what I would do is draw an arbitrary axis. Like here's A. Okay. And my z component is my z axis. My z component is going to be what for A? M sub s h bar, which is going to be what number times h bar? 1/2 h bar. And is it going up or is it going, in other words, if this is my center, it's going to be the upper part. So on your ruler here, whatever you'd pick, this has to be 1/2 h bar, or 1/2 centimeter, or 1/2 inch, or whatever you want to call it, right, to make it easy to draw to scale. And then I have to draw it so that this length, right, so here's the 1/2 h bar, that arrow has to be, what is it going to be? What times h bar? A 1/2 times a 1/2 plus 1 square root h bar. What is it, square root of 3/4 or something? Right? So figure out what that is, and then make that length. See what I'm doing?
Yeah.
So you'd label that, then you'd label this one. But you can't just draw them. You have to actually measure it, make it drawn. Make things drawn to scale.
This one?
Essentially, yeah, we're doing that. Exactly. and do that for A, B, and C.
And wherever L is, that's where you plug in 1/2.
That's why I like this expression better.
It can be L or S.
Yeah, and it can even be other things that we're going to talk about later. So this is just a nice general way of the magnitude of blank momentum. Just put in the word. So that's its magnitude. And if you're really good, you could draw the cone thing, but it's kind of asking too much.
Will we have that on the test?
Drawing that cone in 3 dimensions
I mean,
with L equals 6. It's going to be hard, man. You guys might as well give up right now. And woman.
Sharply's down, man.
I could say, dude, confirm that wave functions for a particle in a ring with different values of the quantum number m sub l are orthogonal. What the heck? How are you going to do this? Yeah, what's the... Okay. You're getting there. It's the general starting point. What does orthogonal mean?
Isn't it when there's equal positive and negative parts?
Yeah, the positive areas and negative areas. That's the concept. When you plot this out, all the positive area and negative areas, they cancel out. You get 0. That's why we have the 0 there.
Is it the integral of psi star?
There it is. Integral of...
Psi star. Zero at the bottom.
A little, okay, well, whatever. I don't think you should put a 0. I think you should put... What's 2 little letters you can count for 2 different, like... A and B, right? Just say that 2 things are different. Just use A's and B's. Whatever you want to use, 1s and 2s or whatever. But I think A and B sounds better. Right? That's your starting point. If you pick 2 different wave functions and you integrate them over all space, you better get 0 if they are the O word, orthogonal. So they want you to find some wave functions for a particle in a ring. And where were those at? Yeah. Yeah, there it is. Can I make that big so you can actually see it? Ooh, nice. There it is. Okay. Now you can pick some really ugly ones. They said with 2 different, what? 2 different what? I forgot the question. Quantum number m sub l. Okay, so you could pick some ugly ones or pick some pretty ones. Which ones could you pick here? Now they said 2 different m sub l values. That means they probably want, I would assume, they want what to be the same?
L?
L. That's what I'm thinking. They want L to be the same, but 2 different m sub l's. They probably should have said that. So I mean, you could go way down here and pick, 3 and 2 or something, or even do the same one twice, 3 and -3. Wow, this there's a lot more stuff in it. I think I might pick this one. I don't know. They all look ugly. Right? So I would write the 2 wave functions out. Right? Like, for example, if you pick this one, +1 and -1. So m sub l is +1, m sub l is -1. Right? Or you could pick m sub l +1 and 0. M sub l equals 0. This needs to be the same L, but 2 different m sub l's. So you've got 1, 2, 3. You've got 3 wave functions to pick from. Just pick any 2. And then you write each one.
Is the +1, like if you do +1, you would go minus all of that because plus.
Oh,
minus.
I think you're right. See, if you follow this, if you pick +1, that means that you have to pick this minus sign, and you got to pick this plus sign. Right? If you pick m sub l to be -1, you got to pick that plus sign and that minus sign in the exponential. Okay.
We only integrated in terms of feet. Because it says here the only variable of integration is feet.
It is?
Well, it says him.
But there's theta.
There's. Oh yeah, there's thetas in there. You can't
Oh,
say.
yeah, your hint says only variable is theta.
It does? That doesn't make any sense.
Go up. There's your hint.
That's 14b.
Yeah, so
We're
we're
doing
doing
that
that
one.
one.
We are?
Yeah.
Oh, we are. But that doesn't make any sense.
Does it matter which one we choose to be size star?
Oh, because you're just supposed to, this would be so much easier if we had the book. Okay, so if you look at 14, okay, so you just got off of doing 14. Okay, so imagine this. You just got done doing 14. You figured out what little n is. So now you have the wave function for the motion of a particle in a ring. You have it. You're done. Psi equals whatever you got, e to the I ml phi. Okay, now the next question is, well, show that two wave functions for a particle in a ring of different m sub l are 0, right, orthogonal. Right? Read the 14b question. It fits perfectly. Then it's obvious. You're supposed to use this.
Twice?
Because what does the I'll copy paste it and you'll see what I mean. Where's 14b? Ah. Here's 14b. God, it's going to take all this stuff. Okay, well, I won't get the 1. That's okay. Copy. Let's clean up this mess here. Where's my pen? Can't see anything in the dark. Okay, let's paste it in here. There it is. Okay, so you just did 14a. You have your complete wave function, right? And then you come down to the next question. It says confirm that wave functions for a particle in a ring. Well, look, it just says particle in a ring. You just figured it out. With different values of the quantum number m sub l are orthogonal. So yeah, it makes perfect sense. I mean, that's all you have is m sub l. So that the question we were going to do would that'd be a good test question, right? But we'll save that. Maybe I can make a homework problem on that or something, or a review day. We can do that one. So all you're going to do is right. Call it m sub l a and m sub l b, or m sub l. Put a prime on one of them. Okay, and you should get 0 out of that. Now we're going to probably have to go back to our concept preview, because how do you take oh no, you can do antiderivatives of exponentials, right? That's not the problem. What is the problem?
Do you have the answer for that normalization constant?
I think yeah, you should get 1 over 2 pi square root.
Yeah.
Okay, I think the problem that you're going to come up with 12.14b is that, you use the concept preview in chapter 12, because you're going to evaluate the integral and it's still going to have an exponential in it. And then you have to turn that exponential into sines and cosines. E to the I phi, you need to turn it into sines and cosines so you can actually make numbers for this stuff. You end up with like 1 minus 1 or something, right? So to turn an exponential, e to the I something or other, into sines and cosines, look at the chapter 12 concept preview. So you start out with this guy. Right? Well, d phi, there's no d tau really, just d phi, right? Start out here, get as far as you can, you do the integral, do all that stuff, then look at the concept preview to get rid of that exponential. Okay? You better go because L's getting mad.